This is a continuation of our series on enhanced irrigation devices. And if you recall, our goal was to try to understand the biological basis of mineralization of dentin and how understanding the nuances of that process affects image interpretation. The second part was to understand something about how specimen preparation procedures can affect specimens differently and how those procedures produce artifacts that affect image interpretation. Then we're going to use that knowledge gained from this understanding to improve our pattern recognition skills. So we've already covered the biomineralization aspect in the prior tutorials. Now we're going to take a look at specimen preparation techniques. There's a lot of factors in specimen preparation that are important to understand if you're going to properly interpret images. The basic steps in specimen preparation are fixation, dehydration, sectioning, and coating. All of these procedures can affect the specimen in ways that changes how the image appears. So the first step in specimen preparation is fixation. Why do we have to fix the specimen? Well, when respiration stops, cellular processes maintaining homeostasis end immediately, within seconds. Energy production stops, cell membranes become permeable, mitochondrial activity ceases, and cell autolysis begins. So cell structure is altered dramatically. So the first goal of fixation is to stop metabolism so that autolysis does not take place. The second goal is to fix structures and organelles in their correct position so that they are not altered. And the third is to make tissue stable so it is not susceptible to fungal infection or putrefaction. Fixation works by cross-linking proteins covalently, so it makes membranes much more stable. The unfortunate thing is that our current fixation does not fix lipids and many carbohydrates, so changes occur in those structures regardless. So many of the proteoglycans and glycosaminoglycans and phospholipids are degraded. As we have seen, those are structures that play a very large role in the mineralization process. Now, there are alternative fixative solutions besides formalin, which is what we typically use. And just to give an example, so you can kind of gain a sense for how it affects image. This paper used different fixation procedures using methacarn, which attempts to preserve the EPS, the extrapolymeric substance structures of biofilms. So when you look at organisms that are fixed in formalin, which is what we use, typically under the SEM, this is what you see. When you use this alternative fixation that tends to preserve more of the EPS protein structures, you get an image like this. So you can see the tremendous differences when the extracellular proteins are preserved, which typically they are not with formalin fixation. Again, this is formalin fixation, and this is methacarn. So it does a much better job of fixing the EPS material and making it visible. Most of our specimens are fixed in formalin. So what you have to understand is when you look at a formalin-fixed specimen, there is a lot that is missing information that you don't see because it is not preserved by the fixative. It is washed away, so to speak. So always in your mind should be, what is missing from this picture? So I want you to start thinking, and when you consider images, you want to know something about how the specimen was fixed. Now, the second step in specimen preparation is dehydration. Because under the electron microscope, there can be no water and the specimen is viewed under very high vacuum. Dehydration produces all kinds of artifacts which can be mistaken in image interpretation. So you have to be aware of how specimens are dehydrated. The way we dehydrate specimens is that they go through a series of increasing alcohol concentrations, starting with 50%, then 70%, then 80%, then 95%, and then 3 times in 200 proof alcohol, and then in HMDS as a substitute for critical point drying. This is typically how we dehydrate our specimens at PERF. So all of these dehydration procedures affect the image dramatically. As an example, here are some teeth that Rick Schwartz sent me that were fixed immediately upon his extraction. So what I thought I'd do is just show what happens when you take a fixed specimen and we section the root. And now you can see the fixed but hydrated pulp. This is what the pulp looks like when you section a root that's been fixed but not dehydrated. But when it was dehydrated, it shrinks dramatically. And this is after a series of alcohol rinses. And you can just take the pulp out and peel it right out of the tooth because it is so shrunken down. It stays intact, it gets hardened, and it peels right off the pulp space, revealing the naked dental wall underneath. And that's what I did in this case. I just dehydrated the specimen and peeled the pulp out. And then we're going to look at the axial canal wall and see what this looks like. So you can see here, there's quite a bit of shrinkage of the tissue. And that's where all the cracking is. It's from the dehydration. And you can see that the predentin is still attached to the surface of the canal and was not removed with the desiccated pulp. It stayed attached to the dental surface. And there you can see a little area where the mineralization front is visible under the predentin. And you actually get a pretty good view of the predentin in its native state, having been fixed and then dehydrated. You can actually see the Tomes fibers going from the predentin into the mineralized tubule. And when you look at all that tissue that's involved in the predentin, and probably the odontoblast cell layer, as well as some pulpal tissue, you can see how deformed it is just from the alcohol dehydration. So it's very difficult to recognize any real structures because they're so desiccated. Even though this did have HMDS procedure done on it, there's no way of really avoiding the dehydration effects. So always in your mind is some understanding of how the specimen was processed and what is real and what is artifact. This is another sample that Rick sent me. And here you can see there's an area that looks like a smear layer. Well, that's where my Explorer brushed against the predentin and created a smear layer as I wanted to remove the desiccated pulp out of the tooth. And when you actually go into this area, you can see kind of the smear layer, which is actually the predentin that's been compressed down by the Explorer tip. So this gives you kind of a sense of how to look at these structures and understand how the processing affects what you're actually seeing. Now, the predentin has been compressed down onto the mineralization front. And here you can see the collagen of the predentin. This is right above the mineralization front, as well as the Tomes processes that are going down into the tubule. If you followed the prior mineralization tutorial, you understand that there's a great deal of tissue here that's been lost. The proteoglycans that are in the tubule have been lost from the fixation and dehydration procedures and are simply missing. They were there, but you cannot see them because they've been removed by the dehydration and fixation procedures. Now, there are some fixations that can preserve the proteoglycan structure. And I'd like to show you what it is that you're seeing when you use those fixation procedures. It preserves some of those disordered proteins and glycosaminoglycans that are inside the tubule that we talked about in the mineralization tutorial. Typically, these are completely lost in specimen preparation, but you can use certain preparation techniques to preserve them, and you can actually see what you're missing. So these are 3 samples. The top sample is where the proteoglycan structure of the lamina limitans is actually preserved, and you can see that it is quite a structure. In the middle section, those proteoglycans have been destroyed by the fixation procedure, but the glycosaminoglycans of the lamina limitans are preserved. And you can see that the lamina limitans is really kind of a sheath-like material around the odontoblast. And then the bottom picture is more of our traditional formalin fixation and dehydration, where you can actually see the collagen structure in the tubule. So the bottom picture is what we typically see, but what we're missing in our imaging is the other 2 top pictures. Here you can see the collagen structure of dentin processed in the normal way. And here, when you're looking at the predentin, you can see these globules here. This is what partially demineralized chalcospheroids look like. This is the collagen substructure, and part of it has been mineralized, where you see this kind of opaque material. So it's either in the process of being mineralized or demineralized in the predentin. And on the mineralization front, you can actually see the outline of the collagen fibrils with their classic 67 nanometer divisions. And here you see collagen in transition, either being mineralized in the predentin or perhaps being demineralized through the irrigation devices that we're using. But you gain a greater sense for what the mineralization actually looks like. I think you can see it's very easy to confuse this with EPS of bacteria. So it's going to look very, very similar. There's no way to really distinguish it. This is calcification occurring or collagen in the process of being decalcified. Again, this is right at the mineralization front of predentin. So you can see quite a bit of mineralization taking place. And you can see the structures in the predentin that have been dehydrated down, and they're sitting on top of the mineralization front here. So hopefully you're gaining some pattern recognition for what you're looking at. You can see some of these chalcospheroids in the process of being unmineralized. And again, right here, it's very similar to the look of bacterial EPS, but this is just the mineralization process taking place in the predentin. And as you'll see, this unmineralization process seems to happen in layers because the mineralization happens in layers as well. And these are chalcospheroids with the collagen substructure visible. And so when you look at this, thinking really is everything that's missing. All of the proteoglycans and disordered glycosaminoglycans are missing from this picture. They have been removed by the specimen processing process. So they're invisible to you, but they are there. And here you can see the collagen fibrils, the starting mineralization, as well as some of the substructure of the proteoglycans in the tubules in the process of being mineralized. This is part of the mineralizing front. My interpretation is that these are little mineralization crystals, actually, or perhaps they are matrix vehicles exported by the odontoblast as reviewed in the mineralization tutorial in reviewing the 3 theories of dentin mineralization. They're about 100 nanometers wide. As the collagen is mineralized, these vesicles appear on the fiber and they grow and mineralize the collagen. I hope these brief tutorials have helped you start on the process, on the goal towards better image interpretation. And now we're going to look at some controlled samples. And then the samples from Dr. Pushpak, and we'll see how you do with your image interpretations.